I have written up here a reaction that is going to follow the SN2 mechanism. What's going to happen here is the hydroxide from the sodium hydroxide is going to be replacing the bromo group. Now, notice this convention for writing our reactants on top of the arrow. This is very common. You'll see a lot of it. If you have a product and you have a solvent that matters, then you're going to see the product on top, the solvent written on bottom. If you're going to react with just the solvent will be written on top. So, doesn't need too much attention. We'll get used to it. In this reaction, I want you to notice something. The bromo here is sticking up out of the board. The hydroxide is into the board. My stereochemistry got inverted here. If I were to draw out my hydrogens, I've got a hydrogen going to the back, and here I've got a hydrogen coming forward. Now, we see this. When we run this mechanism, we see this. And this is this, and the fact that this is a second-order reaction is what allows us to model out the reaction mechanism. And so let's go over what that looks like now. The first thing I want to do is I want to draw a large bromopropane that has all of the hydrogens revealed so we can see what's going on. And just for argument's sake, let's also draw in an exaggerated electron cloud for that bromo group. It's going to be very large. All right, so I have this all drawn out now. It's a lot more detailed than we're going to need to be when we're actually modeling these. It's just for the sake of argument. So notice my sodium is not participating in the reaction. It's a spectator. It's just off to the side. My hydroxide is on the opposite side of my bromo group. My bromo is, it's a very large atom. It has a big electron cloud. So when this reaction happens, I'm going to have a collision between my hydroxide and the carbon that it's trying to attach to. This has to happen from the back. It cannot happen up here because the bromo is in the way. Think of it like the hydroxide is trying to steal the bromine's girl. It's gotta come from the side the bromine is not looking at. If it comes from the front, the bromine's just going to fight it, push it away. It's not going to work. So if this tries to come in from this side, it just bounces off. No reaction. So this hydroxide has to come in from the back side. There is a particular way we draw this. We are going to model this reaction by drawing arrows pointing to what electron pairs are forming a bond and which ones are leaving. So whenever we draw arrows in our reaction mechanisms, our arrows are always drawn from an electron pair to an area of positivity, where that electron pair is going to. So in this case, this extra electron pair, the oxygen, that's giving it that negative charge is going to come from the oxygen, and it's going to be going to the carbon. All right? So I draw an arrow. Look at this curved arrow pointing from that electron pair to that carbon. This is it's very nuanced. It's very important that those are drawn exactly the right way. They're not too hard to draw, but we don't want to draw a straight arrow. We don't want to draw an arrow from the carbon to the electrons. It's always electrons curve to the carbon, period. So the same thing is going to happen up here. As these electrons bond with this carbon, the electrons in this bond are going to go to the bromine. And so when that happens, this bromine gets an extra pair of electrons. And it's going to be drawn like... So that'll be my bromine after the reaction. But what about my new substrate? What about my new organic molecule? Well, we know up here it's going to be this propanol. But since it's attached from the back side, suddenly this methyl group here goes from being pushed away by the bromine to being pushed away by the hydroxide. Same thing on this side. It goes from being pushed down from the bromine to being pushed up from the hydroxide. That's why my stereochemistry gets flipped. So because this attacks from the back side, this whole thing, and you'll hear this analogy a lot, it's like an umbrella in a very strong wind. It's facing in, and then the wind hits it, and it poofs out. The same thing is going to happen. They're facing down because they're pushed away by the electron cloud on the bromine, and then when the hydroxide comes in, they get pushed up. And so when I redraw this, it's really getting redrawn like this. So these get pushed away, all right? So if I do this in my ball and stick models, then I have a bromopropane right here. I can see the green, this is my bromine. I can see that if the hydroxide group tries to come in, it's going to hit the bromine. It's got to come from the backside where it's got room to attack. So it's going to come in from the backside, and it's going to be bonding right here. Now, when it bonds right there, when that bond forms, this electron density, suddenly, this bromine is gone. That stick out of there. And now this electron density pushes these away, and I end up inverting, okay? It becomes inverted. It's very important. That flip in stereochemistry is very important. All right, so let's go over some details of this reaction. First off, notice the flip. We always need to keep that in mind. If I've got some stereochemistry going on, that needs to flip. So let's write that down. Let's make a list of our qualities here. Now that's also useful because if I need a specific stereochemistry, I know if I start with the right substrate, I can get that exact stereochemistry. I'm not going to get a mix of different types. I'm going to get one type. Okay, what else? The other factor here is that this is all occurring in one step. Okay? This bromo gets kicked off because this hydroxide group is coming in. You can really think of it like it's like I don't know, cats sitting on a bed. One cat tries to come in and it pushes the other one off so that it can sit in the bed. So this all happens in one step. This pulls the attention of the carbon away, releasing this bond. All right? So with that said, we really do kind of have an intermediate moment here where the carbon can be said to be attached to both the hydroxide and the bromine. So let's draw that out. Let's draw what that looks like. And in the process, we'll look at how do we model these the way that you'll actually do it, not drawing out all of the hydrogens. All right, so I've got this intermediate step drawn in. So my hydroxide group attacks this carbon, and at the same time, because this is attacking this carbon, this bond gets taken by the bromine. So I draw my arrow, and draw my other arrow, and so I can see in the intermediate moment, as this is occurring, this is not a separate step. This is what this looks like as this step completes. The carbon is technically attached to both the bromine and the hydroxide at the same time. So this is really carbon with 5 connections. That's unstable. It's not going to stay that way. So this is why this is an intermediate step. This is incredibly unstable. It's not going to happen. So it has to break a bond with one of them. It's got to let one of them go. Well, the hydroxide is much better at bonding to that carbon than the bromine is, so it lets the bromine go. See you later, bromine. And so in our last step, we have a hydroxide, a hydroxyl group on my propane. So this now becomes propanol, and that bromine is going to float away in that solvent. That bromine is perfectly fine holding on to that negative charge. It is very stable this way. So this is the actual mechanism for a SN2 reaction. So this is how you're going to be drawing this out. You're going to show the arrows in the first step, in this single step, the arrows being kicked away, all right, from the electrons to their destination. And then you're going to show me this intermediate step. This is going to be, these dotted lines are going to represent bonds that are only half formed. And then you'll show me the end step where everything is fully bonded. The stereochemistry is flipped. You could also draw this. You could also draw this. That's very sloppy. You could also draw this with it flipped up this way, where the OH is going to point into the board. That's fine, as long as you show that this stereochemistry is somehow flipped. So then the bromine is by itself floating away. So this is how we draw this. This is how this mechanism actually occurs. So we can see that it is one single step. So what else do we need to know about this? We need a strong nucleophile. Aprotic solvents are going to be better. In protic solvents, what's going to happen is I'm going to have all of this hydrogen binding. And that hydrogen binding is going to cause my more electronegative nucleophiles to get caught up binding to a bunch of water molecules or ammonia molecules, whichever. And it's going to hinder that back attack from being able to occur. We can see that now. We can see why that solvent is going to hinder that. Because imagine if this hydroxide was surrounded by 50 other water molecules. It's really going to hinder that attack from being able to occur. It's not going to be able to fit in. Likewise, in a protic solvent, in protic solvents, my stronger nucleophile is actually going to be something like iodine, which is already larger on its own. So it's going to have a harder time making that back attack. So keep that in mind. So in aprotic solvents, it's going to work better for the SN2 because we're going to be able to be a little more, we'll say discreet, like a little more sly, like a spy sneaking in order to assassinate a dictator or something. Finally, one of the biggest barriers to the SN2 reaction being able to occur is going to be steric hindrance. And we can see that if we put together some little organic molecules. If I've got something like what we used in this reaction, this is 2-bromopropane. Remember, in order to have the reaction, my hydroxide has to be able to get in and hit the back of that carbon. It's going to be forming a back attack. So this is actually pretty difficult for this hydroxide to get in here. It's going to come in from the top, from the side. It's going to get blocked all around except from that back side. So what's easier? Well, it would be easier if this guy were right on the end. See, now we've got this entire range that I could attack from where I could still get into that back side. Okay? Even easier than that is a methyl group. This, I can basically attack from any angle and still reach that back side. So this hydroxide is going to be attracted. It's going to be an electrostatic attraction to this. So if it comes in from this side, it's going to feel that attraction and move and get it. What's going to make it harder? What would be the hardest? Well, I would have something that's got a tertiary carbo group. This is going to be really hard. The only place, this has to come in exactly from the right angle in order to make that reaction happen. And so steric hindrance is a huge barrier for the SN2 reaction. So we can see that we've got these 4 levels of steric hindrance. The greatest steric hindrance is basically going to fully prevent the SN2 mechanism from being able to occur. It'll still happen, but it happens at such a slow rate that it might as well not happen at all. So for comparative sake, the rate of a reaction with a methyl substrate is going to be in the thousands. With the primary substrate, we're going to be looking at 20 to 100. With a secondary, we're going to be looking at about 1, which isn't terrible. But a tertiary, well, we're going to be looking at less than 0.001. So this will occur at 1,000th the rate of a secondary substituted carbon. So this steric hindrance is a huge deal. All right, is there anything else we need to look at? All right. So these are the basics of the SN2 mechanism. So we'll go over the SN1 mechanism, and then we're going to start looking at how to practice these, how to actually draw out our models, and how to predict which one is going to occur. Start putting that flow chart into action.